Okay, so topics for this week. We've talked about column space, and I wasn't here last week, but I think Elliot talked about null space last week. We'll review column space, null space. Have you heard of the row space? We talk about row space. Basis and dimension of a subspace, and then the complete solution to AX equals B. Okay, quick review of what subspace is. There's questions on homework about showing that certain things are subspaces. So if you take V, a vector space, and U, a subset of V, then U is a subspace if two conditions are satisfied. U is closed under vector addition, meaning if you take V and W inside U, then V plus W is also inside U. And secondly, U is closed under scalar multiplication. So if V is in U and C is any real number, then C times V is in U. So those, they ask you to prove or determine if something is a subspace. You show those two things. Or if it's not a subspace, you show that one of those things doesn't hold. And we talked about column space. If A is an n by n matrix, in the column space of A, we denote by C of A. C of A is it's a subspace. It's a subspace consisting of all linear combinations of the columns of A. All linear combinations of the columns of A. You can write that as just the span of the columns of A. Or since I mentioned that linearly dependent columns don't add anything to the column space, this is also just the span of the linearly independent columns. So for example, I also want to say if A is n by n, then the column space of A is a subspace of Rm. So the number of rows determines where the column space is lying inside, and that's because the number of rows determines the number of components in each column. So if A is like this 3 by 2 matrix, then the column space of A is the span of these two columns. set of all linear combinations of these two vectors, which is a plane in R3. So it's a subspace of R3 because the vectors have 3 dimensions. And it's a plane because there's 2 vectors in the span. Okay, null space is a thing. Again, you take some n by n matrix. The null space, which we denote by n of A. Null space of A is the set of vectors x such that A times x equals the 0 vector. So any vector that when multiplied by A becomes 0, that's in the null space of A. For example, if A is this matrix, 1, 2, 2, 4. Notice that the second column of A is just 2 times this first column of A. We want to find maybe we want to find the null space of A. So suppose X, which has these components x1, x2, is in the null space of A. And that means that 1, 2, 2, 4 times x1, x2 gives you 0, 0. And so if you multiply this first row by x, that's a dot product of x with the first row. So that means that the vector 1, 2 dotted with x gives you 0. And similarly, when you multiply the second row, by x, you also get 0. So 2, 4 dotted with x is also 0. So x is perpendicular to both of the rows. So if we draw that, this means x is perpendicular to 1, 2. This means x is perpendicular to 2, 4. So if we draw that, 1, 2 is like this. So x is perpendicular to that, meaning x is like that. It's also perpendicular to 2, 4, but since 2, 4 is just a multiple of 1, 2, these are essentially the same condition. If you're perpendicular to 1, 2, then you're going to be perpendicular to 2, 4. So these are the same. So if x is in the null space, then it just needs to be perpendicular to 1, 2. So the null space of A is just this whole line perpendicular to 1, 2. This is the null space of A. Any vector on that line. Specifically, it's the line x, y dotted with 1, 2 equals 0, which says that x plus 2y is 0. So it's the line y equals negative 1/2 x. That's the null space of A. Another way to write that is the null space of A is spanned by this vector right there, which is the vector like negative 2, 1. Since negative 2, 1 is perpendicular to 1, 2, the null space of A is spanned by negative 2, 1. So that's 3 descriptions of that null space. Another example, if A is this matrix 1, 2, 3, 1 by 3 matrix, and the null space of A is the set of vectors x, y, z. such that 1, 2, 3 times x, y, z equals 0. But if you perform this multiplication here, then you get x plus 2y plus 3z equals 0. And this set here, this equation describes a plane in R3. So this is a plane. This is the plane x plus 2y plus 3z equals 0 in R3. So we can try to draw that. You can note this product here that I did here is also a dot product of x, y, z with 1, 2, 3. You're getting 0. So that means that the null space is the set of vectors which is perpendicular to 1, 2, 3. So if we draw that in 3 dimensions, x, y, z, maybe that's the vector 1, 2, 3. Then the plane will be like, I don't know, it's kind of hard to draw, like something like this. All vectors perpendicular to this one. So you got that vector, got this vector. It's a beautiful picture. That's a plane in R3. So notice if A is m by n, then the null space of A is a subspace of Rn, number of columns, because you're taking any vector in the null space and you're multiplying it by A. So in order to take an m by n matrix, and multiply it by a vector, the vector needs to be n by 1. So it needs to be in Rn. So Rn is the space. So like in this example, A was 1 by 3. So the null space was a subspace of R3. Okay. The row space of an n by n matrix is the column space. You can denote it R of A. It's the column space of A transpose. So just turn the columns into rows and the rows into columns. And then boom, column space of A transpose. So in other words, it's the set of all linear combinations of the rows of A. So if you understand what column space is, then you know what row space is as well. If A is m by n, then the row space of A is a subspace of Rn, because the number of columns will determine how many entries are in each row. I'm going to do an example that's similar to a problem on the homework. what conditions on the vector b1, b2, b3 ensure that B is in the column space of A. When A is this matrix 1, 2, 3, 0, -1, 3, 1, 1, 6. So recall that B is in the column space of A if and only if AX equals B is solvable for X. Because solving AX equals B is just expressing B as a combination, as a linear combination of the columns of A. So we basically need to determine for what conditions on B ensure that AX equals B is solvable. So we need to take A and put it and augment it with B and do some raw operations on both sides and see what happens. So we can do, I want to reduce this to a 0, so we can do row 2 minus 2 row 1. I also want to reduce this to a 0, so I'll do row 3 minus 3 row 1. So if you do that, this is 0, -1 minus 0 is -1, 1 minus 2 is -1, 3 minus 3 is 0, that's still 3, and then 6 minus 3 gives you a 3. B2 minus 2B1, so we get there, and then B3 minus 3B1. Now I just want like this to be 0, but notice that the third row is just -3 times the second row, so you're going to get a row of zeros here when you do row 3 minus 3 plus 3 row 2. Yeah, you get a row of zeros. This is B1, B2 minus 2B1. And this entry here will be B3 minus 3B1 plus 3 times B2 minus 2B1. Which ends up being B3 plus 3B2 minus 9B1. Okay, so that's that. In order for this to be solvable, you need this thing to be 0. In order for this equation AX equals B to be solvable, you need this to be 0. Otherwise, you would have 0 equals 1 or 0 equals 2 or something. It's not 0, and that would be a contradiction. You would have no solution. That would be like the permanent breakdown. So we need this to be 0. So that's the condition we can put on B. So the condition is B3 plus 3B2 minus 9B1 equals 0. Does that make sense? Okay, let's talk about basis for a subspace. So say V is a vector space, and U is a subspace of V. So we got this big vector space V and smaller guy U. A basis for U is a collection of vectors U1 up until UN, in U that satisfies two conditions, or I'll say which are linearly independent and span all of U. So a basis for U is just a collection of vectors in U that span all of U and are linearly independent. This condition means U is the span of U1, U1. So some examples of basis would be, we can find bases for the column space and the row space and the null space. So if A is an m by n matrix, then a basis for A, for column space of A, basis for the column space of A is the set of linearly independent columns. Basis for the column space of A is linearly independent columns of A. In other words, the columns with pivots. When you do row reduction, you reduce it. You determine which columns have pivots. Those are the linearly independent columns, and those columns form a basis.
So, is the basis for the column space of A just the column space of A?
No. The column space of A is the span of the columns, the set of all linear combinations of the columns. But the basis is just like a couple of the columns. So like if A is, like we did before, this kind of matrix, then the column space of A is the span of these two columns. And a basis for the column space of A is just these two columns. So not the span, but just two columns. Basis. So this was like a really kind of simple example, but you can imagine if there's like 10 columns or something, then it could be kind of difficult to determine which of the columns you need for a basis. And so in that case, you would do row reduction and find which ones have pivots. A basis for the row space is just the linearly independent columns, or linearly independent rows, since we're talking about row space. Basis for the row space is the set of linearly independent rows of A. So that's the rows with pivots. Okay, so a couple examples. A basis for R3, three-dimensional space, is the three standard unit vectors, perpendicular axes, unit vectors along the axes. That's a basis for R3. So they're obviously independent, and you can write any vector as a combination of those. Another basis for R3 is, well, it could be something like this: 1, 2, 3, 0, 1, 1, 0, 0, 1. So two completely different bases for R3. So there's infinitely many choices for a basis. But notice that in both of these situations, I had exactly 3 vectors in the basis. So that's a general fact. Any basis will have the same number of vectors in it. Any basis for a specific vector space will have the same number of vectors in it. So let me write that down. Fact. Any basis for a subspace, a particular subspace, will have the same number of vectors in it. So any basis for R3 will have 3 vectors. Any basis for R2 will have 2 vectors. So this set here is not a basis for R3. Because this last vector is dependent upon the first 3. You can write it as a combination of the first 3. So these vectors are not independent. You have too many vectors, basically. You have 4 vectors, too many vectors. But if you change it slightly, if you take away one of the vectors, maybe like this set, this is also not a basis. Because there's too few vectors. You can't get every vector in R3 as a combination of just these 2. So there's too few vectors. So they don't span. So in some sense, a basis has just the right amount of vectors that you need to describe the vector space. Since any basis for a subspace has the same number of vectors in it, we could define the dimension of a subspace is the number of vectors in any basis. The number vectors in any basis for the subspace. Since they all have the same amount of vectors, this is a good way to define it. And it also aligns with the way we usually use the word dimension. When we talk about the dimension of R3, we usually say it's like 3-dimensional space. So if you use this definition of dimension, then the dimension of R3 is 3, as it should be. And the dimension in general of Rn is n. So it makes sense. Okay. So let's do some examples where we determine if a set is a basis. Example, determine if this set of matrices this way, 0, 1, 0. Is a basis for M2, 2, which is the set of 2 by 2 matrices. The vector space of 2 by 2 matrices. So we need to determine, are these matrices If we think about them as vectors, are they linearly independent? And do they span all of M22? So these guys are independent if you take a linear combination of them. And you get 0. If that equaling 0 implies that these are all 0. So they're independent if this condition is satisfied. The only linear combination of these matrices that gives you the 0 matrix is the 0 combination. That's what we need to show that they're independent. Or if they're not independent, then we need to show that there's some non-zero combination that gives us the 0 matrix. So if you write out this like system of equations for the first component in each matrix, we'll get a system of equations. We'll get a single equation for that first component. So we'll get 2c1 plus 0c2 plus c3 plus 3c4 equals 0. And then for the second entry, we'll get 0c1 plus c2 plus 0c3 plus c4 equals 0. For this bottom left entry, you'll get 0c1 plus 0c2 plus c3 plus c4 equals 0. And then you'll get c1 plus 0c2 plus c3 plus 2c4 equals 0. So we could try to solve this for c1, c2, c3, c4. Or you can convert it into a matrix equation and it might look nicer that way. And then we can just do row reduction, reduce the matrix. So maybe we want this entry to be a 0. Should I swap rows maybe? Because as it stands, I would need to do like row 4 minus a half of row 1, but I don't want to deal with fractions. So maybe I'll just swap these two rows, the first row and the last row. You can do that. So then we'll do row 4 minus 2 row 1. One minus 2 gives you a -1. And 3 minus 4 gives you a -1. And then we'll reduce this to a 0, but the last row, row 4, is just -1 times row 3. So we'll get a row of zeros here. So we'll do row 4 plus row 3. And you end up with a row of zeros. So this row of zeros means that we don't have a pivot in each column, because there's not a pivot here. There's not a pivot in this last column. So this matrix doesn't have full column rank, meaning the columns of the matrix were not linearly independent, which means the matrices to begin with were not linearly independent. And another way to see that is C4 can be anything, and this equation still gives you 0 equals 0. So C4 is a free variable. They can be anything, and the equation will still give you 0 equals 0 at the bottom. So as long as C1, C2, and C3 are chosen properly, then it'll work out. Well, yeah, okay. Yeah, so in this condition here, C4 doesn't have to be 0 here, basically. So since this condition is not satisfied, that means that these matrices were linearly dependent. So the matrices are linearly dependent, which means this set does not form a basis, because they need to be independent to form a basis. So the matrices not independent. It means not a basis. Does that process make sense?
Is it not independent because the last row doesn't have a pivot?
Yeah, that's true. Yeah, the last row doesn't have a pivot, so the columns are not independent. The columns are dependent, so the matrices are dependent. Okay, another example would be if you take some like polynomials. Because the polynomials of degree 2 or less form a vector space. So you can talk about a basis for that vector space. Determine if this set of polynomials is a basis for P2, which is the set of vector space of all degree 2 or less, 2 or lower polynomials. You can't say the set of all degree exactly 2 polynomials, because that's not a vector space. But you can say degree 2 or lower. So we need to check that these are independent. So we'll check independence. So again, we'll do like the same thing. We'll take a linear combination of these guys. And set it equal to 0. But if we like distributed these all out and then compared the like grouped together all the degree 2 terms and all the degree 1 terms and then all the constant terms, if we compared the coefficients, then it would be basically like setting up a linear system of equations, right? Because this on the right hand side is just a polynomial where every coefficient is 0. So if we distribute this out, and and we group together the x squared terms. So the x squared term would be c2. This is an x squared term, and that's an x squared term. So c2 plus c3 x squared. And then we'll group together all of the linear terms, degree 1 terms. That's degree 1, that's degree 1. So this is going to be c1 plus c2, 2c2x. And then all the constant terms together. So the constant terms are going to be 2c1 plus c2 minus c3, and as everything is equal to 0. So in order for this polynomial to be equal to 0, all the coefficients have to be 0. So that means that c2 plus c3 has to be 0, and c1 plus 2c2 has to be 0, and 2c1 plus c2 minus c3 is 0. So we get, again, just a system of linear equations. And so we can write it as a matrix. Let's see, 0, 1, 1, 1, 2, 0, and 2, 1, negative 1. So just like before, we can just turn the problem into a matrix row reduction, pivot finding kind of problem. And if you compare this matrix to what the polynomials were up here, this first column, the first column of this matrix corresponds to this polynomial here. It has 0 x squared coefficient, it has 1 for the coefficient of x, and it has 2 for the constant coefficient. So this first column corresponds to this first polynomial. The second column of the matrix corresponds to this polynomial here, x squared plus 2x plus 1, because there's a 1 here for the coefficient of x squared, and a 2 for the coefficient of x, and a 1 for the constant term. So you could have just looked at the problem and gone straight from that to this matrix equation, just by looking at these coefficients and reading them off, and basically putting these polynomials as the columns of this matrix. But this process is why that works, why it works out that way. Okay, so we want to basically find the pivots of this matrix and determine if these columns are linearly independent. So we'll do some row reduction. Maybe I'll swap columns again. Yeah, so I'll swap columns, and I'll just augment this with zeros instead of writing C1, C2, C3. Then I'll do row 3 minus 2, row 1. 0, 1, 1, 0. 1 minus 4 gives you negative 3, and negative 1 is here. And then we'll do row 3 plus 3, row 2. So negative 3 plus 3 gives you 0. Negative 1 plus 3 gives you 2. So this matrix has a pivot in each column and each row. So it's full column rank. 3 pivots, meaning the columns are linearly independent, so the polynomials we started with are also linearly independent. Linearly independent. So that's independence. Next, to check span, we need to check if every degree 2 or lower polynomial can be written as a linear combination of these other polynomials. So an arbitrary degree 2 or lower polynomial looks like ax squared plus bx plus c. Let me write that over here. Ax squared plus bx plus c. And I want to write that as some combination using coefficients like d, e, f of those polynomials we wrote down earlier. Do x squared plus 1 or x squared minus 1? X squared minus 1. Okay. Okay, so this, if you can solve this equation for d, e, and f in terms of a, b, and c, then that means that these polynomials span the vector space. So the goal is to solve for d, e, f in terms of a, b, c. If you can't solve it, then it means they don't span. So again, we can distribute these in here and group together the quadratic terms and group together the linear terms and compare the coefficients of the polynomials we get on both sides and get just a system of linear equations. And so it'll be just reduced to another matrix equation. So if we did that, we would get that and that and that. So we can combine the x squared terms. The x squared terms are here and here. So that's e plus f times x squared plus linear terms are here and here. So that's 2e plus d times x. And then constant terms are here and here and here. So that's 2d minus f plus e. Two d plus e minus f. So if we compare the coefficients on both sides, the coefficient of the x squared terms, those need to be equal to each other. So a needs to be e plus f. B needs to be 2e plus d. And c needs to be 2d plus e minus f. So we have a system of equations. We can convert it to a matrix equation again. We get 0, 1, 1. Wait a minute. 0, 1, 1. That's not right. It should be DEF. Yeah, so 0, 1, 1. That's right. This one is 1, 2, 0. 2, 1, negative 1. Okay. So that's the matrix equation. So if we compare that matrix to the matrix we found earlier, yeah, this matrix here. It's the same matrix, 0, 1, 1, first row, 1, 2, 0 on the second row, and then 2, 1, negative 1 on the third row. So it's the same matrix as before, but now the only difference is that we have ABC on the right-hand side. It's not just 0, 0, 0. But we already determined that this matrix is full column rank. And since it's a square matrix with full column rank, that means it's invertible. So in order to solve for D, E, and F, this matrix is invertible. We can solve for D, E, and F by just taking the inverse of this matrix on both sides. Solve for D, E, and F. It's just the inverse of this matrix times ABC. And since we can solve the equation, that means that the polynomials do span P2. So you could figure out what D and F are explicitly, but that would be a lot of work. And we know it can be done, and that's the important part. So these polynomials span all of P2. So that's spanning and independent. Spanning and independent. So it's a basis. Okay, let me do a problem where I find the basis for column space. And row space. Okay, so we just need to figure out which of the columns is linearly independent, because the basis for the column space is the linearly independent columns. So we'll do row reduction. We'll reduce A. We can reduce this to a 0. So we'll do like row 2 minus row 1. We can reduce that to a 0. We can do row 3 minus 3 row 1. And then 3 minus 3 gives you 0. 1 minus 6 gives you negative 5. 7 minus 12 gives you negative 5. And negative 2 minus 3 gives you negative 5. Okay. And so the third row is just a multiple of the second row. So we can reduce that to 0 by doing like row 3 plus row 3 minus 5 halves of row 2. Not super important what the operation is, but we can do it. So now we know what the pivots are. The pivots are this 1 and this negative 2. So that means that the first two columns are linearly independent. And these second two columns are not independent. They're dependent upon the first two. So these are independent. And these are dependent.
Can you explain why?
Why what?
Why those who are independent and those who are dependent?
These first two are independent because they have pivots.
Okay.
And the second two, the last two are dependent because they don't have pivots. Okay, so that means a basis for the column space of A are the first two columns of A. Let's see, what was it was 113, 201. Those were the first two columns of A. So that's the basis for the column space of A. And basis for the row space of A, just like column space, the first two rows have pivots, and the third row does not have a pivot. So the first two rows of A are a basis for the row space. You can write them as rows. Doesn't really matter. Or you could write them as columns. So the dimension of the column space of A is 2. Since there's two vectors in the basis, the dimension of the row space is also 2. So that's a fact that holds in general. Dimension of the column space is always the same as the dimension of the row space. Those are always equal. And we call that common number the rank of A. So the rank of A is equal to the number of pivots, the dimension of the column space, the dimension of the row space, the number of independent columns, the number of independent rows. Those are all the same number. Okay. What about finding a basis for the null space? Let's do that. Dimension or basis for null space. The steps are reduce your matrix to reduced row echelon form. Identify the pivot columns and then the columns without pivots, which are the free columns. Figure out which ones those are, and then solve for pivot variables corresponding to pivot columns in terms of free variables. That's the general procedure. So for example, take this matrix 1 1 1 1 3 2 2 0 2 4 2 2 negative 2 1 3. So it's a 3 by 5 matrix. We want to find the null space of A. Find a basis for null space of A. So the null space of A is the set of vectors so that A times X equals 0. So we're basically solving AX equals 0. So we'll take A and we'll augment it with the 0 vector. And we'll convert A to reduced row echelon form. So we can do like row 2 or row 3, or it doesn't really matter. We'll do row 2 minus 2 row 1 and row 3 minus 2 row 1. So if you do that, you get a negative 2 here, you get a 0 here, you get a negative 2 here. Row 3 minus 2 row 1 gives you zeros here and here, and a minus 4 here, and a minus 1 here, and a minus 3 here. And then zeros still augmented. Now I want this negative 4 to be a 0. So we'll do row 3 minus 2 row 2. Negative 3 minus 2 times negative 2 is negative 3 plus 4, which is 1. Okay, so this is like row echelon form. But if you want reduced row echelon form, so these are the pivots. These are the pivots. That's a pivot, that's a pivot, and that's a pivot. It's the first non-zero entry in each row. But if you want reduced row echelon form, then you also want this one to be a 0, and you want this one to be a 0. You want zeros above and below all the pivots. So we'll go a little bit further I'll do row 1, row 1 plus half of row 2. And then you get a 0 here. 0 here. And then you can do row 1 plus row 3. So you get a 0 here and a 4 here. Okay, so that's reduced to echelon form. Those are pivots. Some people require the pivots to be 1s, but it doesn't really matter that much. It won't change your answer in the end. Okay, so well, I'll write out the system of equations we have right now. This was ax equals 0. But really this is 1, 1, 0, 0, 4, 0, 0, negative 2, 0, negative 2, 0, 0, 0, negative 1, 1 times x1, x2, x3, x4, x5 equals 0, 0, 0. And so if you write out this system of equations, you get x1 plus x2 plus 4x5 equals 0. Negative 2x3 plus negative 2 minus 2x5 equals 0. And negative x4 plus x5 equals 0. So we have these three equations for the reduced system. And we also have some of these are free variables. X2 is a free variable, so it doesn't have a pivot in that column. Pivots are here. X5 is also free, because there's no pivot in that column. So we can say X2 is like a free variable t, and X5 is like s. And so we want to solve for X1, X3, and X4 in terms of t and s, the free variables. So if you rewrite this equation, the system of equations, you get X1 is minus X2 minus 4X5, but that's the same as minus t minus 4s. X2 is t. X3 from this equation is negative x5, which is negative s. X4 is x5, which is s. And x5 is s. So from here, you can like factor out all the coefficients of the t's and factor out all the coefficients of the s's. So this says x1, x2, x3, x4, x5 is t times, coefficient here is negative 1, so you get negative 1. Coefficient here is 1, so you get a 1. And then 0, 0, 0. For the s's, you have negative 4 s's, 0 s's, negative 1, 1, 1. And these two vectors are called special solutions. In the null space, these are special solutions. And they form a basis for the null space. So the null space of A say basis for the null space of A is -1, 1, 0, 0, 0, -4, 0, -1. Why did everything go wrong? That's pretty bad. -4, 1, 1. That was what it was. I don't know what happened. That's the basis.
Is reduced row echelon form the same as upper triangular?
I don't think so. Yeah, so like here,
Or just not reduced, just row?
so I'm not sure you mean by row echelon form. Some people call this row echelon form, this matrix. So that would be like upper triangular or row echelon form where you have zeros below each pivot. But this is reduced row echelon form where you have zeros above and below each pivot.
Can you think of row echelon forms as upper triangular?
Yeah.
Okay.
Yeah, as far as I know, like row echelon form is the same as upper triangular, just for not square matrices. Okay, so something's weird happening, but that process makes sense? Finding the null space? Okay, because that's pretty important. You'll be doing it for like the rest of the semester, finding null spaces. Okay, so let me do a quick thing about finding a complete solution. And to make it faster, I will use the matrix we just did. So let's say we want to find the complete solution to AX equals B, where A is the matrix we just did. And B is, oh shoot, I gotta find something in the column space of A. Okay. Let's search for the pivot columns. Let me do 2, 2, 0. Yeah, 2, 2, 0. Okay. So there's like 3 possible cases for solutions to AX equals B. Either you have one unique solution, or you have no solution, or you have infinitely many solutions. So this complete solution thing has to do with describing all possible solutions in the case that there are infinitely many solutions. So the complete solution is x equals xp plus xn, where xp is one particular solution that solves AX equals B. So you could, if you wanted, you could just like try to guess for what it is. That would work. And then xn is the general vector in the null space. So basically the special solutions, a linear combination of the special solutions, is a vector in the null space. So xn will be like t times one special solution plus s times another special solution. That's what xn will be. So since we've already found the null space of the matrix, we've already done like most of the work. So xn in this case is t times that first special solution, which was -1, 1, 0, 0, 0, plus s times -3, 0, -1, 1, 1. And for xp, we can try to guess for a particular solution. Xp just satisfies ax equals b, that equation. So b should be, yeah, b is a vector, and so b is 2, 2, 0. So that can be written as the first column plus the third column. Just eyeballing it, 1, 2, 2 plus 0. What was it? 0, I just looked at 0, 1, 0, -2. So that means that a particular solution is 1, 0, 1, 0, 0. Because I'm using 1 of the first column, 1 of the third column, and 0 of the others. So a particular solution is 1, 0, 1, 0, 0. So that works. But there's obviously infinitely many choices.
Can you explain one more time what was 1, 0, 1, 0, 0?
Yeah, so I'm writing b, the right-hand side, 2, 2, 0, as the linear combination, as this linear combination of the columns of A. So the columns of A the columns of A were these guys. I was using this column plus that column. And so xp is the vector 1, 0, 1, 0, 0, because I'm using 1 of the first column, 1 of the third column, and 0 of the others. So that's why xp is that. So that means the general solution, the complete solution, it's a set of vectors, really. You get a different solution for every value of s and t that you choose. So that's the complete solution. But there's like a lot of different answers that would have been valid here. Any questions?
So it was -4, not -3.
Is it negative? -3?
It
This
was
3?
-4.
-4
Yeah.
in the basis for the null space? Oh, it was -4. Why was it -4? Is it supposed to be -4? I had a -4 here. Okay. Yeah, it should be -4. Thank you.